Hi, good morning. Indeed, it was not 10 seconds. It's usually 6.5, but I count on my fingers, so I apologize. So good morning for you. I would say good afternoon. Yeah, just a little moment. We have 6 p.m. here. So if I mix morning and afternoon, that's due to the difference of time zones. Sorry, Emilke, your turn.
Thank you. So I'm thrilled to be here with you for the virtual visit to CERN, the European Organization for Nuclear Research. This tour is interactive, so feel free to ask questions anytime. Just raise your hand. Today our guides will be Noemi and Zoltan. Thank you for hosting us.
And we also have Cedric here. He is not on. Well, okay.
Hi, Cedric.
He is our safety guide today, and he is also participating.
Okay, so I now pass it over to you, and so we can get started.
All right. So, all right. Good morning. Okay, this time I didn't screw up. Right. So, I would say that probably we should start in the middle where we are. Let me just remove your camera and then add what I just wanted to show. So that's the bird's eye view of the region where we are. We always communicate that we are at CERN, which is technically true. Geographically, this is a little bit more complicated. So what you see on the picture is the Geneva Basin. You might see the Mont Blanc just in the background, the highest mount of Europe. In the foreground, you see the Lake Geneva. You might see the town of Geneva, the runway of the Geneva International Airport, which is something like 3 kilometers. So you might have a little bit of a feeling, despite the distortion of the image. And you might see several interesting things. For example, this little stuff here written CERN. This is one of our campuses. We have 2 big campuses and several smaller sites. This is not one unique place, what we call CERN, and that's why I said that geographically this is a little bit more complicated than what people used to say or think. So this is the main campus, and you might also see this dashed line here, and that's the border between France and Switzerland, and that's also the border of the European Union, indeed. And that cuts through the main campus, so creates very interesting international situation. We can also talk about it later. You might see 2 colored lines, this blue stuff and the yellow stuff here. The blue stuff is the superconducting proton synchrotron or superproton synchrotron. This is a 7 kilometer long underground thing. This is something that is with us for something like 40 years now, and was responsible or played a crucial role in the discovery of the W and the Z bosons. We can also talk about that later. But the reason why we are here today is one part of this yellow stuff, which is called Large Hadron Collider, which, as you might also see, 27 kilometers long. So this is the biggest accelerator that has ever been built in human history. Of course, this is also an underground, so obviously we just show it on the picture. It has 4. Let me just try to go there. Yes, exactly. It has 4 large underground points. We name them where after the experiments that are hosted in. Yes, exactly. The Atlas. This is at point 1. This is the closest to the main campus of CERN. Actually, these are acronyms. A toroidal LHC apparatus. Sorry about physicists responsible for these acronyms. CMS is the compact muon solenoid, so nothing to do with the mass. Okay. Alice, a large ion collision experiment. which is responsible for the heavy ion collisions, just about a minute, and LHCb, which is LHCb, and this is also a special thing. So among these 4 large experiments, 2, the ATLAS and CMS, are so-called general purpose proton-proton collider experiments. We are the Santa Maria of the expeditions, of the discoveries. These are the big ships that sail out on the ocean and try to find the way to India. Sorry for the beyond standard model word. And we will see what we will find. We already found part of India, Higgs boson, but also we are open for new discoveries. The 2 other experiments, the ALICE is more interested in colliding heavy ions. In every year, something like 1 month, we spend for colliding not protons, but rather totally stripped lead ions. Actually, we already trying to do it with oxygen and xenon, but that's a different story. But usually it is lead ions. So 2 big stuff that we smash together in the experiments, and actually, I would almost said hope. Actually, this is now a fact, an experimental fact, that we see the absolutely special type of the matter. This is the so-called quark-gluon plasma, where the quarks and gluons, the constituents of the hadrons, the proton, for example, neutron, for example, they fly in a soup, and they are not bound to the baryons. This is something very interesting material, and we believe that this was dominating the universe very soon after the Big Bang. The LHCb, the 4th experiment, they do not play in our league. Actually, we both, the ATLAS and CMS, has heavy ion programs as well, so we also stick our nose in this business. But the LHCb is something really weird. It seems that the word works a little bit on a chiral way. Left-handed and right-handed, especially leptons, are not the same, having not the same role in particle physics. This is one of the biggest enigma, and we want to understand this is it better. This is also somehow related to the charge parity conservation, and this experiment is built for experimenting on this, especially on those events, on those things, on those measurements where the B quark, that's why it is B, the B quark pops out from the collision, as those mesons that are containing B quark are very, very sensitive for the charge parity conservation, or the non-conservation of the charge parity. So that's a very interesting thing. They have several very interesting results. Besides of this, they also discovered that not only 3 quarks can be in a bound state, but also 5 or 4. That's a very interesting thing. We could talk about it later. So these are the 4 inhabitants of this world here, and we are currently sitting at the compact muon solenoid, far, far away from the main campus. So again, something for this specialty of how CERN is geographically built up. Indeed, we are something about 7 kilometers away from the main campus, but technically we are on a CERN site. And actually below my feet, I'm just at this moment sitting in the control room of this experiment. So below our feet, something about 100 meters, we have the beast that is currently, what is the status? Do we have a beam inside?
A squeeze, yes.
We have a squeeze. So actually we have We have proton beams in the yes, exactly. We have proton beams in the accelerator. Sorry, I just wanted to make a. I will find it later. We have Noemi and Cedric with us, as I already told you. They are going to start up the mobile camera in a second, and they will make the most interesting part of this tour. I think it is much more visually much more exciting than what looking at my face.
But let me tell that we cannot go to the experimental cavern because there is proton beam in the LHC. But we can go underground and see the service cavern where we can see some nice interesting stuff. I think. We have to wear safety equipment, helmet, safety shoe, and for the access I have to wear my personal dosimeter, which contains my iris data, and you will see the access fed in 2 minutes. How we enter.
Before going down, do you want to go around in the control room just to show around this this very nice installation? Actually, we got it last year. Before that, we had something much smaller. Sometimes I feel that a little bit more familiar, but this one is very spectacular and very grandiose. All right. In the meantime, just to tell you the same what your teacher said, that this is not a formal talk. This is not a formal session. If you have any questions, please don't keep it in there. Ask immediately. Cut us. Okay? Great. I think I will just replace.
Can you see my image?
Yes, perfect. You are on the screen.
Okay, so this is the CMS control room, and we have so-called shifters to control the experiment. So there are different different responsibilities. We have here with lots of screens the so-called technical shifter. He's responsible to make sure that all the detector elements, sub-detector elements are on. We have cooling, and everything is safe, and no fire alarms because the detector and personal safety equipment is also.
Sorry for sticking my nose in, Noemi.
Yes.
Indeed. I just want to say that what we have is one of the biggest things that have ever been built in the human history. We have something around 120 million measurement channels, independent measurement channels, and this has to be fed with infrastructure. All of them require some low voltage to keep them alive. Some of them are relying high voltages around. Some of them need gas, different types of gases. Some of them needs cooling, maybe all of them. So this is indeed what is governed here. We have something like 5 million data points that we have to watch 24/7. Actually, if our shifter would need to do it by himself, I think he would be worn out very quickly. So indeed, we have an expert system behind, and the human intervention is needed only if the system cannot solve the problems itself. But obviously, we do not run it without the shifter. There are some other aspects that Noemi started to tell, and I let her to explain.
So we have the technical shifter here.
Zoltan, I have a question. We can see on the right of the physicist who is sitting there, a book. What is it for?
You mean in the middle, that one?
Yes, right.
Exactly. That's our problem-solving stuff. So obviously, we work by procedures, and in case of anything special happens, we have a written procedure. We are very similar to the airplane industry, you know. So if we have anything, we try to avoid to rely on the shifter's intuitions, because it might be wrong in case of a havaria. Instead, we have accepted procedures that the shifters follow, and also they have the most important phone numbers there, names there, contacts there that are quite that might be important. They are not alone.
Thank you.
Noemi, just go ahead.
Yes, so we have also not just the person responsible for all the technical details, but here we have the shift leader person who keeps in contact with the accelerator, the control room, and also he knows what is happening in CMS. So he is the boss of the shifters here in the control room. We have the DAQ post here. This is the screen to start the recording of the data. And we have here the trigger shifter, who is responsible for the trigger system, and we can tell about it later. What is it?
Exactly. That's something that I want to talk about, or we want to talk about later. But that's a very important part of that. Yeah.
And also the DQM shifter post responsible for the quality of the data.
And I'm just sitting close to there. Hey.
So these shifters are here so we operate the detector 24 hours per 7. So each shift post is 8-hour long shift. And of course, over that, we have on-call shifters as well for the subdetector subsystems and technical stuff as well.
Exactly. This is not the full control room. For the subsystem, so-called subsystems, they have their own posts behind. They are not always populated, but we have the possibility, or the experts have a possibility to sit down in front of their own screens and deep dig a little bit in the system if they wouldn't do it from home. We will also talk about it later when we are going to talk about the detector itself. So Noemi is following the way to the surface installation, and we might also lose her. That's due to the nature of the wireless communication. And that's the reason why I'm here. Otherwise, I would let her to do it. Noemi, where are you?
So I'm at the access So he used his personal dosimeter, which contains his iris data, to go in. The pad opens for him as soon as he badges. It measures that it's only one person here, checks the iris, and then if everything is okay, he can go in. Also, there is a trick in this door that it detects. It wants to detect that only one person, the person who badge, goes in. So therefore, to go in with the camera, it's a bit complicated, but I will try to solve it. Okay,
I just have one comment. Please mind the color. We will get back to this later. Sorry, I just repeating myself. This is at least the 5th time now that we are going to get back later. And also I wanted to tell that this fuss about of the accessing, that's quite a, yes, we lost them. That's quite an important thing. We have an experiment down there that uses high voltage gases. There is some radiation on the ground, of course, not everywhere, but obviously we do not allow everybody to go down out from the street. In order to get access to the underground zones, we all have to have several trainings that we have to renew regularly. We have to have our dosimeter. We have to have our medical follow-up. So that's quite an important thing. On the other hand, also we have quite a value down there. But I used to say that if it had wings, it would be the space shuttle. So indeed, and that's unique on the other hand. So obviously we want to protect both the unexperienced people from the experiment and the experiment from the malicious guys as well. So Noemi, take the, yeah, go ahead.
Do you hear me? Because I was lost.
Yeah, exactly.
So we call the elevator. It's already here on level 0. So we go ahead to level -2 because we go underground. So we have 3 levels in CMS. This everything is in service cavern, and okay. The distance between 0 and -1 is about 80 something meters, and between the levels -1, -2, -2, -3 is about 5 meters. But you will see the display of the elevator.
Exactly, and the peculiarity of this radio communication is that on the way down, we are going to get disconnected. And yes, exactly, this happened right now. So I will replace with my own picture and with this special thing. And of course, on the way up, we were not experiencing any cutoff. That's very, very strange. We are roaming between 2 countries. That's a technical detail. What I'm playing at this moment for you guys is the map of the underground region. Noemi is getting underground in this vertical shaft. We call it PM54 after the French name of the vertical shaft and the machine. And the 5 is here that we are the 5th point. And 4 is that we are towards the point 4 from the collision point in the detector. As you might see, we have 2 big characteristic things, or 3 big characteristic things. This underground cavern, we call it USC 55, underground service cavern 55. This is where Noemi is going to access now through this vertical shaft. And there is another, which is called UXC, underground experimental cavern, where the detector is. As we just said, that if I would open this, the vista page of the accelerator, you might see that we are full with beam. Actually, I wouldn't call it full. We have 10 bunches as I see. So we are far from being fully populated in the accelerator, but the accelerator is running, and that means that that people cannot access the caverns. So indeed, we are going to stay in here, and in between the 2 underground caverns, there is a quite thick, something like you will see, 7.2 meters thick concrete, iron concrete pillar that actually the primary reason for putting it in was that the rock around is quite light. We had to reinforce the zone in order to cope with the 2 underground caverns. One is 55 meters and the other is 80 something. So this is really big installations, and indeed we had to support it somehow. But the side effect of this wall is that this wall shields very nicely the radiation. Therefore, we can access all the time in there. And that also makes a kind of a shielding of the magnetic field that allows our equipment to be put in this service cavern. Right. I think Noemi is back online. So I think
yes.
I just do replace to her.
I want to show, I don't know if you already see it, but so I'm next to the elevator shaft. So we have a shaft where we can transport with crane big objects underground. So what you can see, this light on the top of the screen is the surface building. So I'm really 87 meters underground. And you might see, it's very hard to see, but that is the -3 level.
Can you just look through between the panels?
What I try is this.
Yeah, try not to drop the camera. Yes, exactly.
No, I don't drop it in. So so this is -3, and you see that there is a wall. That is a movable wall. So during the year-end technical stop, which is 2 months, 2.5 months, we can do some upgrades in the detector, and for accessing we need cherry pickers and scissor lift, these big lifting devices, and they are usually transported through this wall. But during the runtime, what we are now,
I mean, this wall is removed and retracted.
Yes, but this is sliding, so it's
exactly.
It's some hours job to open it or close it.
Exactly. Nothing explains better its function than its name. It's called plug.
Yeah. So I'm heading towards the counting room, where we have our electronics for the detector. So as Zoltan said, this is a place where we can be anytime, independent from the LHC.
You can even bring in visitors.
Yes, but visitors are not allowed between the rack rows, but I can go in. So here you can see equipment like power supply for high voltage, also equipment for data taking. All these cables are fiber optical cables, computers. So these equipment should be close to the detector and should be accessible. So this is why we have this room here. And
just an example. Oh, sorry.
Two rooms.
Yeah, exactly.
So we have one room here in -2 and one similar size room in -1. So yes,
just an
go
example.
ahead, Zoltan.
Power supplies. So as I mentioned, we have an electronic detector, so we need to power it somehow. Power supplies are very special creatures on the globe. They obviously they cannot be placed arbitrarily far from the detector, because the losses will be so huge that indeed would not be handleable. But they unfortunately cannot stand two things. One is the magnetic field and the other is the radiation. So that's something where we had to make a compromise. That's why we had to put them out. Also, the front-end electronics that you might see there and some of the backends of the data taking, these are very, very highly dense electronics that usually no one wants to put in the radiation fields. But again, they cannot be arbitrarily far again from the detector. So that's why we group them in these counting rooms. As Noemi said, we have 2 levels, one here and one above this room, and they are in this underground cavern. As we just mentioned, this underground cavern is not subject of a radiation. Therefore, we can bring in even visitors during the year time. We have something like 30,000 visitors in these installations in every year. What do we see now, Noemi, now?
So I just came also a place where no visitors allowed. This is below the 4th floor of this electronics room, what we visited. So you can see the lots of cables. All these goes to these blue racks. And the way is, of course, it should be connected to the experiment. And how we do it, the cable goes down in 3 vertical shafts. Unfortunately, it's hard to see that, but this is quite large shaft and goes below the detector, and then it comes up on the experimental
Actually,
cover.
this is a chimney. This can be regarded as a chimney. We have 3 of them. I would like to show something to the audience. Actually, we are working in a reverse order. I'm fully aware of this, but I'm also excited. But I would like to show you this picture. Just put it next to that. That's the schematics of the detector, and that's the beast why all the fusses that we do around, we do for. What we have to know that the protons or heavy ions travel in this beam pipe towards to the detector center, and really in the middle of the center, the beams that are coming from that direction and the beams that are coming from this direction collide with each other. And of course, if a physics is made there, I mean, if the collision produces anything that is interesting, again, footnote, interesting, we will talk about it later, should be observed. But I have to confess something about. And this is that you probably, or surely you heard about the W bosons, the Z bosons, and recently the Higgs boson, and you also heard about that Nobel Prizes were awarded to the experiments or the theorists who invented these, at least the concept of these particles. And you know that among them, the Higgs was also discovered in this detector that you see in front of you. The confession part is that despite we know and we are sure that these are existing physical objects, I mean these particles, nobody could see them any time in the history such a way as they would fly through the room. And the reason for this is that even though these are really existing particles, they do not live forever. They are not stable particles. They decay after a very short time. This very short time is characteristically something like 10 to the 20, 10 to the 10 to the minus 20, 10 to the minus 23 seconds. So it means that extremely short time after their creation, they decay. So quickly, if we regard the 10 to the minus 23, that even if they would fly at the speed of light, they don't do because they are very heavy. If they would fly at the speed of light, they wouldn't fly more than the diameter of a proton. So we have no chance to see them as they are flying. They wouldn't fly out even the proton beam that creates them, not talking about the beam pipe, the high vacuum beam pipe. So they would not reach even the inner part of the detector. What else can be done in this case? Actually, what we can do in this case, that if something is not stable, it should decay to something else. And if we observe this something else, we measure the physical parameters of this something else, then we can try to reconstruct what happened really in the middle. What is this something else? This something else are particles where the let's say the Higgs decays into. Actually, what you see on this picture is a physical, a tiny little physical experiment of a collision of two protons where we believe that a Higgs boson was created and it decayed into two muons and two photons, indeed. Actually, what do we need to measure? We need to measure where the particles fly away. We need to measure what energy they take away, of course. We need to measure what is the momentum they take away. And also we have to get a hint what type of particle it was. So you might imagine that's the main task of these detectors. That is a problem though. And the problem is that if you want to measure the flight path of a particle, you try to interact the minimum with this particle. You do not want to interfere with its flight path, but of course you want to know where it flies away. So this is a tiny little interaction, but you do not want to change its energy. Instead, if you want to measure the energy, you want to take away the full energy of the particle. You want to absorb it. That's the maximum interference. So one might have an impression that this cannot be done with one homogeneous detector material. So that's the reason why we are built up like the shells of the onion. I'm not talking about the stinkiness, but also the different detector types. So on the next slide, you might see one slice of this detector. If the collision point is somewhere here in the middle, the particles fly out radially in this radial section, and you might see the different detector parts. The innermost part is the so-called tracker. This is made up of a silicon semiconducting device. This is very similar, especially the inner layers are very similar to your camera. Actually, I'm pretty sure that you have several hundreds of megapixels in your room at this moment. We have something like 80 megapixel. The difference between your camera and our camera is that while your camera has one distinct layer, one CCD, where where the camera measures the incident photons. Instead of that, we have 10 cylinders, concentric cylinders, where we can measure not only at one point, but at several points as the charged particle flies away. So we might have a three-dimensional view of the particle. And the other big difference is that even if you have the best super duper phone, in a burst mode, you can take something like 10-ish, maximum 20 photos after each other. You know, this is very important if you want to make a photo of your cat at home. In our case, our detector can make 40 million photos per second. So indeed, that's a little bit superior in technology, but this is important in order to make a track of the charged particles. Only the charged particles can leave a message in this detector. Behind that, we have two so-called calorimeters. Actually, CMS is built up of this way. We have one crystal calorimeter consisting of something like 77,000 of lead wolframate crystals. It is sensitive for the electrons and photons. I'm not going to go into details how it works, but it creates light, and the light flash intensity is related to the incident electrons or photons energy. And there is another calorimeter made of brass and scintillators. You might see that this is something like sampling. You take samples of the shower that is created by those particles that contain quarks. So something like the pions, the kaons, some protons, neutrons that fly away.
Sorry to interrupt you, Zoltan.
Yes, go ahead.
How many times do you repeat an experiment to get a reasonable data collection?
That's a very good question. Thank you. So indeed, the problem with physics, let's start with the problem of physics and the problematic of why we had to build this giant stuff around us. The problem with physics is that what we are looking for is extremely rare. The Higgs boson, according to the configuration of the accelerator that time, something like 10 years ago when we discovered it, was something like statistically we got one Higgs boson created in every 3,000 billion proton-proton collisions. So you might imagine that this will not happen every moment. In order to get a statistics, and as you said, it is very important, as we cannot tell exactly from each photo what we see there, but based on the different physical parameters and based on the difference of the statistical difference of these physical parameters from the so-called background events, we can have a hint that we saw a significant excess of Higgs or not. This is quite complicated to explain, but what is the takeaway from this is that this is a statistical game. So in order to have a paper, in order to have a discovery, we have to get many collisions, and we have to get quite a lot of something like what you see on the picture. So in order to do that, we decided to fill our accelerator maximally with 2,800 bunches in each direction of the collision. These bunches meet each other 40 million times per second inside the detector. This is the innermost part of the detector. And from these bunch collisions or collisions, we have something like 30 to 70 individual proton-proton collisions. And this is needed in order to get enough statistics to be able to show that we found the Higgs boson. So you might imagine that actually the processing of this enormous amount of data was really the challenge of the LHC experiments. So okay, that's the story. Indeed. So that was the colorimetry. Sorry, I'm switching back because I want to give Noemi the dance floor pretty soon. So indeed, that was the colorimetry. You might see that in the colorimeter, we stop the particles. We don't stop one, and I will tell you that another one we don't stop either. The other one is the neutrino. We don't even show here. The neutrino is a very light and very weakly interacting particle. This doesn't interact significantly with our detector. We can detect it only indirectly based on the energy and momentum conservation of the particle experiments. We also have another particle which is charged, so it leaves a trace in the tracker. And also, if we put ionization chambers outside, can do ionization. This is called muon. This particle can fly through several meters of material. Actually, below 100 meters below, if we have 100 meters of rocks above, we can still see cosmic muons with the detector. So obviously, we are not going to stop it. But since it is charged, if we apply a very strong magnetic field, we can bend the path of the particle, actually not only the muon, but also the other charged particles. And from the bending, the Sagitta measurement can tell us the momentum of the particle, and that's good enough for us. And if you look at this picture in global, you will see that from the different positions of the colorimeter signals, or the muon system signals, or the curvatures, or the non-detecting particles, we might have the impression of what type of particle was it. So we can do the measurement of all the four. Right. So that's what we want to do indeed. So I give back the dance floor to Noemi, because she would like to show you something very important. Indeed, yes, but again, mind the color behind.
Yeah.
and
so
and
this
she will
is
explain.
Do you hear me?
Yes, of course.
Hello?
Go ahead.
Okay. So I'm in another access door, but as you see with the red colors, the red blinking stuff over there, it's not possible to enter. So this is same type of access pad. So this is the limit between the experimental and the service cavern, but the color means yellow, so it's not always accessible. And when we have a short access or a long access period, like winter time, we can badge in and go in like what we did in the surface. Also, this is one of the closest point to the experimental cavern. So that wall over there is the 7-meter thick wall, what Zoltan mentioned in the picture. And we have some magician tricks here, because what you see, our magnet is on the 3.8 magnet.
Before you would show the magic, let me just tell the audience that I will not let you how, but obviously you would figure it out. If we would break through this door,
yes,
it would immediately shut down the full 27 kilometers of the accelerator. That's a very important safety measure. If there is any Havaria inside, let's say, a fire. We never had, but we are prepared for. And the fire brigade needs to go in. They will not fiddle with the beam dump. They will not fiddle with calling any other people to do something and open up the experiment, etc. They would just break through. But by the time they would go in, the radiation would drop, and this interlock that is built in the door would prevent the restart of the accelerator. And that's partly the reason for the color. So the yellow means those doors that are interlocked, but in some cases you can get through, and there will be also a red one. Noemi will show it on the way out, which is always interlocked, and this can never be get through. Okay, that's quite an important thing. There is also something in this door, what is very interesting, that if we can get access during the so-called runtime, when we can expect, yeah, exactly. So this time it is closed. This door would give you a key. This is again another level of safety. So it is not just enough that you badge with your dosimeter, you identify yourself at the iris scanner, but you would get a key from those boxes Noemi showed you. And these keys also are doing a hardware interlock to the beam permit. So if the keys are not back, if not all the keys are back, then the accelerator operator cannot inject any beam in the LHC. This is quite a strong thing, and we are very sensitive and strict on this. We don't want to get any problems, any accidents of this. Actually, Noemi was very shy to show that she's completely filmed. There are cameras all around, and we are recording what is happening to that. So if anybody would dare to make any jokes, I think we would immediately find. There are cameras outside, cameras inside. So surely you would be filmed. All right, Noemi, sorry for again sticking my nose in. Go ahead.
Sorry for forgetting this to explain. So the magic trick, because I'm so excited about this. I have a very interesting magnetic sensitive equipment. This is called paperclip. It's a very cheap one. So you don't see anything like this. But if I put another one, then it attaches. And I'm just close to the wall, about, let's say, 1 meter away of this 7-meter concrete and iron wall, and I can go close and still it attach. And if I go away, at some moment it will drop. I still have some field. So it's, what is the field there? It's not huge. It's just some milliteslas. And instead, you see it start lowering.
Exactly.
And at some moment it should drop.
it would fall apart.
Yeah.
Hopefully. Oh,
no.
Yes. Okay.
Physics works. And now you see an opportunity that here is the red door, this interlock door, what you mentioned, Zoltan.
So actually, yeah, exactly. So this door, we never open. If we need to open it, we open it only for exercises, but this is not used regularly. And that is, yeah, exactly. This door is for the emergency exits. Exactly. If we would break through this door, that would again inhibit the accelerator. We are not going to demonstrate it today.
It leads to the LHC tunnel, and
also another small
elevator.
And also a very small elevator. So if for any reason we would not be able to escape through that elevator that Noemi came in, we would be allowed to break the door through and get to the small elevator. Obviously, this would be an event that we would classify as an accident, and that would be investigated later, of course.
And since this place is also where we can welcome visitors, we have this poster, since we are not allowed to bring visitors in the LHC tunnel, even when there is year-end technical stuff. So here is a poster where visitors can make a nice selfie like it would be in the LHC tunnel. So you can see the accelerator units, the bending magnets, or this big blue stuff. And also if Cedric come close with the camera, you can see that it's really, really curved. So the tunnel is really go.
But that's called the circular accelerator. Right. Okay, I would ask for questions, Amuka.
And I think in the meantime, I go in the surface to see the life-size poster.
Okay, that would be great. That would be great. Okay. Amuka, questions?
Do you have any questions? No? Then yes, we have. So how do you collaborate with scientists from around the world, and what are some challenges of international research?
Actually, when the CERN was created, it was created to overcome all these political differences that we experienced before. We wanted to create, I can use it in this plural form as we, as I feel myself part of it. We want to create an environment where everybody from this globe can get together and can concentrate on the research only without doing any politics. This is one of our mission at this institute. We also want to be able to freely spread the knowledge. As you might see, we try to show everything to you guys that allowed, at least by the safety, and only the safety that governs our camera today. So indeed, this is quite an important thing. Technically, CERN was created in 1954 as an European institute for the European countries to join, and there was only 12 at the very beginning who joined. Obviously, the communist sector didn't do that, but we came after the system changed in 1989. Nowadays, we have 27 member states, and we also have several observer states. Just to name some of these little observer countries: United States, Japan, Russia, and I think Canada as well, something similar to this. They also contribute in the research, and what concerns the detector operations and the detector development, these countries are fully in, regardless that they are not full CERN member states, okay? So for example, what concerns the CMS experiment, we have more than 150 collaborating institutes with more than 5,000 people from all over this globe. That's a very important thing, from all over. And that makes a very, very working, very living international scene here. So I think that's the answer on your question.
Thank you. Thank you. You can repeat it loud because
what's your individual role at CERN, and what do you do there?
Amuka, could you please repeat it?
What's your individual role at CERN? What do you do?
Besides the virtual visits that you observe at this moment. So, together with Noemi, we are involved in several little projects of the CMS experiments live. We are responsible for the so-called hardware muon parallel alignment system, whatever it means. That's an important thing. I'm also participating in one of the new detector deployment and production called GEM. These are gas detectors for muons. These are gas electromultiplicator detectors. Okay, I was just looking for the abbreviation correct. Noemi is also involved in the so-called survey of this detector. So you might imagine that this is a 16-meter tall detector. You will see the life-size poster actually on the second picture. And we have to know its detector parts, and when we put it together, we have to be sure that we do not crash anything. We can totally fit. We can do it precisely down to 1-2 millimeters. That's a very huge task, and one of the collaborators in this group is Noemi. But apart from this, we are sticking nose here and there. We do mainly these technical things there, but we are physicists, and we made our PhD partially also in physics.
Thank you.
How did you get to work at CERN, and what do you like most about your job?
Can you hear?
If you could repeat that, I would appreciate it.
Louder, please.
How did you get to work at CERN, and what do you like most about your job?
How did you get to work at CERN, and what do you like most at your job?
You mean every day? How do I get here? I come by car.
How did you get the job?
Yes. Oh yeah, okay. That's I think that's most important. Indeed, when I was a student at my home university in Debrecen, Hungary, that a team from there was involved in the late so-called L3 detector of the late Large Electron Positron Collider. That was the previous flagship project of CERN. As a student, I got involved in that, and somehow I stayed. I stayed for the other project of of my home institute. That was the muon barrel hardware barrel alignment, and at some point with Noemi, we had to come out here as a resident, a permanent resident, and continue our work first on the alignment, and then on several other small projects here. And somehow we just stuck here during the past just something like 16 years. Yeah, exactly. But the answer to your question is very simple. If you are at your home university, you have to get in contact with a group who is participating in any of the CERN experiments. I would say that this is not a big deal, because practically every university on this globe somehow participates in this. And then you just join that group, and sooner or later you will find yourself out here, because we do need the souls. Yeah.
Can I interrupt for just 1 minute?
Sure. Go ahead. And I put you on the full screen.
Yeah, just to show that this is a life-size poster, and so made of, I don't know, thousands of pictures. So this is how it looks like when it's open. The end cap is open. So I just want to show you, if I go there close, what is the size. So this is 15 meters in the reality.
Yeah, exactly. Let me just show at the same time, again, the schematics of the detector. So if we would cut the detector at the plane somewhere here, you would see this picture that you see there. You see the inner part of the detector. On your picture, it is some golden stuff. That's the tracker. Around the tracker, you see the electromagnetic calorimeter ring. Then in blue, you see the hadron calorimeter. The big silver ring around is the 3.8 Tesla superconducting magnet, which is the biggest on this globe that has ever been built with this magnetic field. The bore size is something like 6 meters. So that's extremely huge. And outside of this, the red stuff, what you see is the iron yoke in order to encapsulate this field outside. And also it is interleaved with the silver boxes that are the muon chambers of the muon system in the barrel region. Yes, exactly. And actually on the picture, yeah, go ahead.
Yeah, so you remember that Zoltan showed you that we have a big shaft. So this is the top of that big shaft. And this is a concrete plug, which can be slide over the below the poster.
Below the poster, yeah. This is something like a 2 meter thick, rather iron than concrete stuff. We used, actually at this moment, this is hermetically sealing the detector cavern, so no air can come in, come out around it. But this is, as Noemi said, that when we can access to the detector, we can remove it, and the overhead portal cranes can reach in and can put in, for example, those stuff that you might see, this yellow stuff that is needed as an auxiliary construction in order to reach inside the tracker region, or those little cherry pickers that we often use to reach several parts of the detector. With Noemi, we both have the license to drive that. Very funny.
Okay, in the meantime, I go back to the control room and look the outside area, the mountain, and then you can answer the questions in the meantime.
Exactly, I would give back the voice to Emilka and the class.
Any question? Then, what are some of the future projects or goals for CERN? I know you cannot talk about everything, of course, but some goals.
Yeah, exactly. So indeed, there are several different steps for the future. The closest step is to renew our detector, make it even more granular, inflate up the channels that we have. I mentioned 120 million to something like, I heard the number, I was a little bit astonished, 2 billion. I hope it is true. So it means that we could have even better pictures about, indeed, better measurements, what happened inside. At the same time, we are going to upgrade the accelerator as well. And the reason for that is that, okay, we found the Higgs boson, but so far we didn't see anything, even the clue of anything else beyond the so-called standard model of particle physics. We know that this theory is not complete. There are several open questions in there, and for the answer, we have to of course, observing and measuring things behind it. The problem is that we didn't see them yet. There might be one thing that they are extremely rare, and we just simply didn't see them because of the lack of statistics. So the easiest thing that we are going to do, we try to increase the statistics. That is the so-called high luminosity LHC project that's going to start, I mean, the realizational phase, not the design. The design is almost ready by now. The building phase will start sometime at the mid next year, during the so-called large shutdown, long shutdown 3, which will take up something like 3 years without beam. We will completely upgrade the accelerator, and we will get something like 5 to 10 times more collisions, 5 to 10 times more data out from the accelerator, and we might have the hope to see something, even if indirectly. Indirectly means that we measure something that cannot be completely described by the so-called known physics theory. This is something that we expect to last until, actually, according to the latest LHC plans, up to 2041, when we plan to stop our accelerator, and we will try to build something completely new called, actually the work name of this is Future Circular Collider. That will be something like 90 kilometers in circumference, and that will be partially under Geneva, under the Lake Geneva. This ambitious project will crank up not only the luminosity, but also the energy of the collisions, something like 7-fold, up to something like 100 tera-electron volts. And there we hope that we will find something from the new physics. So actually, that's the answer to your question, America.
Thank you. Then, what are some of the most significant discoveries made at CERN? Just a bit summary that the student can remember of this.
Actually, there are physics discoveries. We already mentioned the discovery of the W's, discovery of the Higgs, the discovery of the Z's, that are fundamental to our present knowledge of the physics of the particles. But also, we have to tell you that there were some other very interesting things, like the discovery of the quark-gluon plasma, or at least some physical. Yes, the sun shines on your face, Noemi, very much. But also the quark-gluon plasma, and also the studying of its physical properties. Also, there were many non-physics things that are happened to be, I wouldn't say discovered, but rather invented here, that you have a use in your everyday life. Actually, there is something very easy. That's the World Wide Web. You probably know that this was invented here somewhere around 1990. The reason for that was to speed up the information exchange among physicists in the large physics experiments. That time it were several hundreds of people, but if you regard the email was not the fully optimal thing to exchange information. So indeed, it was invented here, and then it somehow got out to the wide, and that completely changed our life. We use it at every level of our life. I don't need to explain. We also have several new technological achievements in radiotherapy of the medical parts, also the medical imaging, not to tell just the PET camera, the positron emission tomography camera, that is nothing else but a crystal calorimeter that we run here. So actually, this is something very important. Also, there is something completely new, and usually, despite or apart from these that I just mentioned, there is something completely new, and now we can talk about. This is the high temperature superconductive power lines that are developed here, especially for the high luminosity LHC. This development might also reform the long range energy transport. That, of course, will have an impact on your everyday life. So indeed, that's a kind of a interesting lab. Also, if we are talking about superconductivity, the superconductivity is quite a complicated technological challenge. But of course, if you just regard that it should be done by a company, a business oriented company, then of course it would regain the money invested on this from the customers. If it is done by CERN, indeed, that's happening here. And if we would just share this information or share this technology with the big players in the industry, then this would not need it to be charged on the customers. So indeed, this is again something that you might profit of in your everyday life.
Thank you. Then one last question. What role do computers computer simulations play in the research conducted at CERN?
Large. Indeed. Indeed, as I told you, if you take a look at the physics, the collisions, the micro experiments that we conduct, you cannot tell what is it exactly. As I told you, you can make decisions only based on the statistical parameters. I mean, measuring quite a lot of things and make the distribution of a physics parameter that you might think distinctive. And if it is describing the theory, then you prove the theory. If not, you reject the theory. How do you check if the theory can be proven or rejected? This is something like the computer simulation. Indeed, we are running not just our big detector downstairs, but we are also running its simulation down to the microphysical processes. How, for example, a photon loses its energy in the colorimeter by microprocesses, scatterings, ionization, pair production, Coulomb scattering, whatever. So this is something interesting. This physics simulation should be run because there you know what you start from, you know your theory behind, you know what particle you created, you know how it will evolve, and finally the simulation's result is something similar. I mean, technically it should be similar to what you measure in the detector. We try to simulate the measurements of our detector. Of course, this is also a statistical process, so we need to make a simulation for several millions. What is the thumb rule? 10 times more than the measured data that is needed for a good physics measurement. And in this case, we can just simply compare the physics parameters that we simulated to those that we really measured. This looks a little bit complex this way, but indeed, yes, it is.
Thank you. Then, yeah, we have 5 more minutes left. So I just would like, thank you so much for that incredible tour. We really appreciate the time you took to share your knowledge and experiences with us. So it was fascinating to learn about CERN. I hope you all enjoyed this presentation as much I did.
At least remember, I enjoyed.
I remember to take the curiosity and excitement you felt today and keep exploring the wonders of science. And thank you again, Noemi and Zoltan. We hope to connect with you again in the future. Köszönöm szépen. Mindkettőtöknek, Noemi és Zoltan. Fantastic.
Thank you so much for joining us for today. And actually, you saw that this topic is extremely complex. I would also enjoy to continue our discussion, and also we could get into the details a little bit more. Actually, of course, limited by my knowledge, but we could go into the details, and we could continue this talk. Thank you very much for joining us. Köszönöm, hogy itt voltatok. Szervusztok, kellemes napot. Ciao, ciao.
Nektek is köszönöm szépen. Bye.